Constraints on sine and cosine values. Welcome, everyone. Today, we are beginning a new subsection where we will explore the mathematical limits of the sine and cosine ratios. You might wonder why we need to study these limits. Well, understanding these specific constraints is absolutely crucial. It allows you to look at any given trigonometric value and immediately identify whether that value is mathematically possible or if it is logically incorrect. Over the next few slides, we will use the fundamental properties of right-angled triangles to prove exactly why these limits exist. The fundamental property of a right triangle. Now, before we dive into the specific limits of sine and cosine that we mentioned in the previous slide, we need to ground ourselves in a fundamental property of geometry regarding right-angled triangles. Let's start with the basics. In any right-angled triangle, the side that sits directly opposite the 90-degree angle is known as the hypotenuse. Now here is the key logical point. Because the right angle is, by definition, the largest angle in the triangle, the side facing it, the hypotenuse, must always be the longest side of the entire triangle. To make this more concrete, let's look at a triangle delta ABC where angle B equals 90 degrees. In this specific triangle, the hypotenuse, AC, will always be longer than the opposite side, BC. Similarly, the hypotenuse, AC, will also always be longer than the adjacent side, AB. If we were to write this out mathematically, we would state that BC is less than AC, and AB is less than AC. Keeping this relationship in mind is essential, because as we will see in the next few slides, this is exactly what creates the mathematical boundaries for our sine and cosine ratios. Analyzing the sine ratio, \sin A. First, let's look at the definition of the sine ratio for an acute angle, which we will call angle A. We define sine of angle A as the side opposite to angle A divided by the hypotenuse. Using the labels from our previous slide, we can write this as the length of side BC divided by the length of side AC. To make sure this concept is crystal clear, let's go through a step-by-step logical breakdown. First, we identify our components. We know that the numerator, which is side BC, represents the side opposite to our angle. Second, we know that the denominator, side AC, represents the hypotenuse. Now, here is the crucial part. As we discussed in the previous slide, the hypotenuse is always the longest side in a right triangle. This means the denominator, side AC, must always be greater than the numerator, side BC. In mathematical terms, we say BC is less than AC. Think about what this means for the value of the fraction. In mathematics, whenever you have a positive fraction where the numerator is smaller than the denominator, the resulting value is always going to be less than 1. Therefore, we can conclude that the sine of angle A must always be less than or equal to 1. This brings us to a very important constraint that we will see applied again when we analyze the cosine ratio in the next slide. Now that we have established that the hypotenuse is the longest side of any right-angled triangle, let's apply this logic specifically to the sine ratio. Analyzing the cosine ratio, \cos A. Now that we have established why the sine ratio is limited, let us apply that same logic to examine the cosine ratio for the same acute angle A. If we look at the definition, cosine of A is equal to the side adjacent to angle A divided by the hypotenuse, which we can write as side OB over side AC. To make sure we really understand why this happens, let's go through a step-by-step logical breakdown. First, identify the parts of our fraction. Here, the numerator, which is side OB, represents the adjacent side. The denominator, which is side AC, remains the hypotenuse. Now, let's recall the fundamental property we discussed in the previous slide. The hypotenuse is always the longest side of a right-angled triangle. This means that the adjacent side, OB, must always be smaller than the hypotenuse, AC. In mathematical terms, we say OB is less than AC. Consequently, because we are dividing a smaller number by a larger number, the value of this fraction can never exceed 1. Therefore, we arrive at our conclusion. Cosine of A is less than or equal to 1. This brings us to the same constraint we found for sine, which we will see applied in a practical, real-world example in the next slide. Real-world example, the leaning ladder. Imagine you have a ladder leaning against a vertical wall. If you look at this setup, it forms a perfect right-angled triangle. In this scenario, the ladder itself acts as our hypotenuse. The height of the wall where the ladder touches is our opposite side, and the distance along the ground from the base of the wall to the foot of the ladder is our adjacent side. Let's look at a specific scenario. Suppose the ladder is 5 meters long. First, let's evaluate the height using the sine ratio. Think about it logically. The height the ladder reaches on the wall can never be 6 meters because the ladder, which is our hypotenuse, is only 5 meters long. If we look at the formula, sine of angle A equals height divided by ladder length, which is height divided by 5. Since the height cannot possibly be greater than the 5-meter ladder, the resulting fraction, height divided by 5, can never be greater than 1. Next, let's evaluate the base distance using the cosine ratio. Following the same logic, the distance from the wall to the foot of the ladder cannot be 7 meters if our ladder is only 5 meters long. When we write this as a ratio, cosine of angle A equals base distance divided by ladder length, or base distance divided by 5. Because the base distance is also limited by the length of the hypotenuse, this ratio, base distance divided by 5, also cannot exceed 1. Now that we have established the mathematical theory behind why sine and cosine cannot exceed 1, let's bring this concept into the real world with a practical example. This real-world example perfectly illustrates the constraints we discussed in the previous slides. Key takeaways. All right, let's bring everything together and summarize the key takeaways from today's lesson. First and foremost, remember the fundamental geometric principle we discussed at the start. In any right-angled triangle, the hypotenuse is always the longest side. This is the foundation for everything else we've learned. Because of this, when we look at any acute angle, let's call it angle A, we can establish clear mathematical limits. When we calculate the sine of angle A, which is the ratio of the opposite side to the hypotenuse, that value will always be less than or equal to 1. Similarly, when we calculate the cosine of angle A, which is the ratio of the adjacent side to the hypotenuse, that value is also always less than or equal to 1. To put it simply, for any acute angle, the values for sine and cosine will always fall within the range between 0 and 1. Now, before we move on, I want to point out a very common pitfall that students often encounter, so please pay close attention to the next slide. Common mistakes. Now, before we wrap up today's lesson, I want to address a very common pitfall that I see many students fall into during exams. The most frequent mistake is assuming that the constraint we just discussed, that these ratios must be less than or equal to 1, applies to all trigonometric ratios. It is very easy to mistakenly apply this same limit to the tangent and cotangent ratios. However, let's correct that misconception right now. If we look at the definition of the tangent ratio, tangent of angle A, it is defined as the opposite side divided by the adjacent side. Notice something important here. In this specific ratio, the hypotenuse is not involved in the calculation at all. Because the hypotenuse isn't the denominator, the opposite side is free to be much larger than the adjacent side. Therefore, tangent of angle A can, and often does, result in a value that is much greater than 1. To make this crystal clear, let's look at a quick example. Suppose you have a triangle where the opposite side is 10 and the adjacent side is 2. When you calculate the tangent, you get 10 divided by 2, which equals 5. And as you can see, 5 is a perfectly valid value. So, remember this key distinction. Only sine and cosine are strictly limited to being less than or equal to 1 because they are both anchored by the hypotenuse as the denominator. Once the hypotenuse leaves the denominator, those boundaries no longer apply.